So this is the end of the 1/8 material that I wanted to just get on video in case it helps you to do the homework tonight. So we talked about the difference between average velocity and instantaneous velocity earlier today. And we did get through this part of it, but I'm just going to go through it again because I wasn't sure that since it was so quick at the end, I wanted to make sure that we understood what we were talking about here. So we had this position function, which was called S, and displacement was measuring the change in position over a certain amount of time. So we put our position function into our y equals and tried to figure out what the position was at 1 second versus 2 seconds, and at 1 second versus 1.5, and then we were trying to figure out an even narrower gap here between 1 and 1.1 seconds. So the easiest way to do that was to look at our table, and I went to my table set and started it at 1 and made my delta, or my change, 0.1. And so that allowed me to see all of that information in my table right away. So I knew that at 1 second, I was at 117 feet high, and at 2 seconds, I was up at 197. So we subtracted that and got 80. Narrowing in a little bit, if I just want to know what happened in a half a second, at 1.5 seconds, I was at 161 feet, which was higher than whatever I was at 117 feet, and so we're doing a subtraction problem there. So we're doing our 161 minus our 117 and getting 44 feet of displacement. And then if we go back and do the 1.1 and the 1, at 1.1 I'm reading 126 feet, 126.44 feet, and at 1 second I was at 117. So again, another subtraction problem, and I'm ending up with a displacement of 9.44 feet. No, I typed that in wrong, didn't I? No, I didn't. 9.44 feet. So there's my displacement. So if I look at instantaneous or average velocity, this was the displacement. This was how the height changed. But for velocity, I want to know how the height changed in terms of how the time changed. The change in the height over the change in the time. That's how I'm going to get velocity, average velocity. So here, the velocity on average was 80 feet per second. In 1.5 seconds, it changed 44 feet, but it was only a half a second interval, 1.5 minus 1. So it changed 44 feet in a half a second. So that means I've got to divide 44 by half, which of course is going to double it to 88 feet per second. And then on the last interval, it went 9.44 feet higher, but only in 1/10 of a second. So the speed of that, I'm taking 9.44 and dividing it by 0.1, and I'm getting 94.4 feet per second. So the velocity of this thing is changing as I narrow the gap that I'm talking about. But that's not instantaneous still. It's still only 1/10 of a second. That's not instantaneous. It's getting closer and closer to instantaneous, but it isn't instantaneous yet. I can't do instantaneous velocity without a derivative. So my derivative is going to help me answer C. My function itself was right here. So its derivative is going to give me instantaneous velocity. Its derivative is negative 32t plus 128. So the instantaneous velocity at 1 second is negative 32 times 1 plus 128. And that should be pretty close to this answer because this was a pretty small gap. This is still average velocity, but 128 minus 32 is my instantaneous velocity, which is pretty close. And the shorter I made this gap, the closer I would have had to this answer. Acceleration is the second derivative of position because it's the first derivative of velocity. Acceleration measures the rate of change in your speed. And so if you're accelerating, your speed is increasing. If you're decelerating, your speed is decreasing. This is measuring that. So that means that I need the second derivative. I need to take the derivative of this derivative, and it turns out that it's a constant. So acceleration, anytime you throw a ball in the air on the earth and you're measuring it in feet per second, your velocity in feet per second, your acceleration is always negative 32. As soon as you let go of the ball, gravity's taking over and it's causing your ball to decelerate. So this is always going to be a constant. It's always going to come from this part of your position function. When does the ball reach a height of 245? Well, that's the answer to this question. The height function, the position function, is set equal to 245. So I'm going to leave that for you to solve. That's a quadratic equation that you should be able to solve. And if you can't, make sure you come see me. So the next part of this lesson, we're looking back to what we were talking about previously about marginal change. We previously talked about taking a function and moving one more unit to the right. So we were going from a to a plus 1. The change in our x value was just 1 unit. This is more generalized. If I move h more units along the x-axis, then in order to approximate how much higher I am at the end of that, we're going to use our tangent line again. So in other words, if I know where I start, I have a starting point on my curve, and I want to move to the right, I want to increase my x value a bit, one way that I could approximate where I'm going to end up is to just hop on my tangent line and see where I end up. And that is what this formula does. Although to me, I think it's easier to think about it this way, like we did previously. We said we're going to have a place that we're going to start, a value that we know. We know the function value where we're starting at a. But instead of having to know the function value at a plus h, we can approximate it by knowing the slope of this line and multiplying it by how far we want to go. So this is the slope of the tangent, and h is how many steps we want to take to the right. So it doesn't have to be 1 step anymore. On the previous assignment, if you looked at it, we started with the function value and added the slope to go 1 step. Now we're going to start with the function value and add a certain number of slopes and end up with our new function value. So what an example would look like is this production example. If we have a function that's telling us the production, how many units we're producing at a given employment level, then this notation means that if you have 5,000 people working, you're going to make 3,000, whatever you're making, 3,000 units will be produced. So 5,000 workers make 3,000 units of whatever you're making. But this statement means that 5,001 workers, so that extra worker, let's make it this way, the 5,001st worker, so that next worker you hire, makes an extra 2 units. So that next person that you hire will add 2 more units to your production level. That's what this is representing, the rate of change at 5,000. If I decide to go one more person, I'm trying to hire one more person, I'm going to get 2 more units out of them. So because this is linear, we can use the idea that, well, what if I don't want to go a whole nother person and see how many additional units? What if I only want to increase my labor force by a half? So I'm going to hire a part-time person. How much will I get in terms of extra production from that half person, that part-time person? Well, we can use the same idea here, and we can say that we're going to take the slope at 5,000 times however far I want to move on the x-axis. How many extra people am I going to be hiring when I go from A to A plus H? And in this case, we're talking about a half. H is a half. So a whole person would give us 2 extra units. A part-time person would give us 1 extra unit. And we can do this because we're on the tangent line where things are proportional. We're not on the curve, we're on the line. And anytime you're on a line, things are proportional. If one person gives you 2 more units, a half a person will give you 1 more unit. And looking at C, same idea, but we want to go backward. Instead of going from A, which was 5,000, and moving to the right, we're moving to the left. We want to fire a person. Our production level is going to go down when the number of people we have is going to go down. So we still want to take the slope because that's measuring how production is changing. But instead of multiplying by a positive number, we're going to multiply by a negative number. H is going to be -1 because H, we call it 5,000 plus H, and we want that to be 499. That's only going to happen with a -1 for H. So we're going to lose 2 units. So production will go down 2 units. And again, this is called marginal analysis, trying to decide what's going to happen to our function when we move up or down on the x-axis. Marginal cost, we've talked about before. Marginal cost function is the derivative of the cost function. If I want the cost and the marginal cost for 10 units, I'm just plugging 10 into the cost function or 10 into the derivative of the cost function. So I'd have 620. Oh, this should be a plus. Sorry about that. So I have 630 units. That's what it costs me to make 10 units. My marginal would be 12 times 10 plus 2, which is 122. That's the extra cost for the 11th unit. That's how we talked about marginal cost, the extra cost for the 11th unit if I make 1 more unit. So if I want to estimate the cost to make 11 units, I'm going to do that by starting at the cost for 10 units and adding on the marginal cost for 10. So what I know it's going to cost me for 10 plus what I'm approximating that extra unit is going to cost. So it would be about 630 plus 122, 752. The marginal cost to estimate the additional cost incurred if the production level is increased from 10 to 10.5. Well, now it's not going to cost me 122 because I'm not trying to produce 11. It's going to cost me what the extra cost would be for 11, but I'm only going to do a half of it. That's my H here. So I'm going to, again, take my $122, but I'm only going to incur half of that cost because I only want to increase by a half of a unit. And in this case, a unit would have to be like maybe 100 items or 200 items, and I'm going to only make half of that. So we're using this as like a weight on our change for one unit. We can do a half, we can do -1, we could do 4, but doing 4 would be a little dangerous because you'd be moving out pretty far away from the curve on the tangent line. So you want to be very, very careful if this is A and you jump onto the tangent line to make your estimate that you don't go too far out, because the further you go, the more wrong you're going to be. That's why we want a marginal analysis. We want to stay in close to the value that we know. And that's the end of the notes.